Howdy students, today we're going to go over chapter 4.3 which covers double angles, half angles, and product to sum formulas. Double angles is exactly what it sounds like, you know, an angle times 2, half angle exactly what it sounds like, an angle times 1/2. Product to sum, it will be how we convert a product of two trigonometric functions and turn them into a sum, and also vice versa. So let's go ahead and start off with the angle sum formula, and that's going to help us build up to the double angle formula. And so here we have cosine of alpha plus beta equals cosine alpha cosine beta minus sine alpha sine beta. So what we're going to do to get a double angle, right, that's an angle times 2, is we are going to take alpha, take beta and replace it with alpha. We're going to make a substitution. So everywhere we see beta, it's going to get replaced with an alpha. So when we write it out, here we have cosine alpha minus sine alpha sine alpha. We'll go ahead and throw the highlights to make it clear where we did our substitution. And so this simplifies down to cosine of 2 alpha equals cosine squared alpha minus sine squared alpha. And this one, it kind of notes, got a similar appearance to the Pythagorean identity, cosine squared plus sine squared, but note that if one of them is negative, namely the sine squared, you know, the odd function, if that's negative, then you're dealing with the double angle formula. And so that's one way to keep them straight in your head. So now we've got the one of our double angle formulas. And we're going to go ahead and use the Pythagorean identity to get our other two formulas. And recall the Pythagorean identity, that's simply cosine squared alpha plus sine squared alpha equals 1. So we'll be making substitution for cosine squared and sine squared in this equation up here. So first one, cosine 2 alpha equals 1 minus sine squared alpha minus sine squared alpha, right? That is our substitution that we just made right here. Again, using the Pythagorean identity. And so this simplifies to 1 minus 2 sine squared alpha. Okay. There is our second one. Now for the third one, again, we have cosine 2 alpha. You know, we're going back to this equation here. Cosine 2 alpha equals cosine squared alpha minus, and now we're going to put in 1 minus cosine squared alpha. That's going to replace sine squared. Right, there's our substitution right there. And this is going to become two cosine squared alpha minus 1. Alright, so this top one, I definitely encourage you to commit to memory. These other two, make sure you're able to derive them quickly, because you don't want to clutter your head with too many formulas, but this one I have started is definitely an important one to have memorized. Alright, so let's go ahead and move forward. We want to get a double angle for sines now. We've got three formulas for the double angles for cosines. Now we want just one for sines. and we're going to use the exact same technique. So again, everywhere we see beta, we'll replace it with alpha. So we're replacing this guy, and this guy right there. And so we get the following result. We get sine of alpha plus alpha equals cosine alpha, sine alpha plus cosine alpha, sine alpha. And so note that we get two like terms on the right-hand side of the equation. So sine of 2 alpha equals 2 cosine alpha sine alpha. And that is our double angle formula. That is all we need. Okay, so that one was a little quicker. Tangent, same thing. Everywhere we see beta, replace it with alpha, so we got a beta here, and a beta here, and then there. And so when we work this through, this is going to become tan alpha plus alpha equals tan of alpha plus tan alpha divided by 1 minus tan alpha tan alpha. Okay, so here's all of our substitutions that we made. And of course, this has the nice simplification of having 2 tan alpha on the top and then 1 minus tan squared alpha in the bottom. And that's our double angle for tangents. Alright, so let's go ahead and talk a little bit about triple angle of sine. Alright, so the sine of a triple angle is exactly what it sounds like. We have a sine of 3 times some unknown angle, which we are using x to represent. And we're going to break this up into angle sum formula. This is a pretty common technique, so I don't want you to focus so much on doing only one type of angle, but so much as being able to apply this to a multitude of different types of problems that are similar. And so what we do is we just break this up into two different angles, sine of 2x plus x. And so note that we've got a double angle on one side, whenever we break it up, and then we have a single angle being represented here. So we just use our angle sum formula. Sine 2x, cosine x, cosine 2x, sine x. And so that's our formula here. And like I said, we've got a double angle going on here and here. So we're just going to use the double angle formula that we already came up with for both of these guys. And so sine 2x becomes 2 times cosine x sine x. Like so. And now we're going to do another substitution here. Cosine 2x. And now with cosine 2x, we've got our choice of which formula we want to use. Our choice of these three formulas right here. We're going to go ahead and go with the top one. But we could just as easily go with one of the other ones. Okay, here's our substitution value there with a little sine x right there. All right, and so this is going to simplify down. And so we have 2 cosine squared x sine x plus cosine squared times sine x minus sine cubed x. And this further simplifies to 3 times cosine squared x times sine x minus sine cubed x. And of course, if we'd use one of the other substitutions back here for cosine 2x, our results would have looked slightly different, but it still would have been the same results whenever you graph them, of course. So moving on, how do you do higher odd multiples angles? Well, basically, whether it's for sine or cosine, you use the same technique that we did here, right? If it's sine of, say, 5x, you break it up where you have at least one even number, right? So this becomes sine of x plus 4x. And you note that we can break that up by a factor of 2, and so this becomes sine of x plus 2 times 2x. And then you just treat it like you would before. You'll have a double angle going on here, and then you have another double angle inside that, and it just keeps working that way until you get down to the most basic components. As you go higher in numbers, it does get a little more in depth, but it is something that you could use to potentially simplify a lot of expressions, which comes in handy when you are, say, if you're programming in some expressions that a computer has to perform a lot of computations in a short amount of time. You really want to be able to reduce that computational expense per permutation. So in general, if you have an odd number, it will have the form like this: sine of 2n plus 1 times x, where n is any positive integer. And then you can break it up like so. You'll have sine of 2 times nx plus x. And then you just go on from there. You would apply your angle sum formula. Like so. And then you'd apply the double angle formulas as we did before. Right, that substitution like we initially did. And then that next substitution right here, like as we did before. Note that we've got whatever value of n is included this time. That's really the only difference. And then from there you could keep simplifying it further down, whether or not that was depending on whether or not it would be necessary, or makes it easier for the problem that you're working on is really the question of whether you keep going or not. All right, so let's go on. Let's go ahead and prove an identity. This is a left hand equals the right hand type situation. So let's start off with the left hand side of the equation, since we have a triple angle hanging out here. So we got left hand side. All right, we got cosine x over cosine x and sine x in the bottom, and in the top we do the same trick that we did up above. We have cosine of 2x plus x. And then we use the angle sum this time for cosines. Cosine 2x times cosine x minus sine 2x sine x. All right. And again, that is the substitution that we made here. And now we're going to go ahead and apply the double angles just like we did before. We're going to apply the double angles right here. and then we'll apply the double angles right here as well. Right. Cosine x there, and then minus, and we're going to go ahead and put our double angle for sine right there. To cosine x sine x, and of course that is also multiplied by our sine x that was just hanging out there. And in the next step we simply distribute this guy to both terms in the top, so that we have cosine squared x minus sine squared x all divided by sine x, and then minus two sine x. All right, since both cosine and sine cancel out with the term in that second guy. All right, now let's go ahead and simplify this term right here. We have cosine of x multiplied by cosine of x divided by sine x, and then minus sine x minus 2 sine x. Okay, and then the next simplification, we have cosine of x multiplied by cotangent, and then these two are the same, so we combine them, minus 3 sine x, which is the same as our right hand side. Okay, so this flows just like we did for the earlier section when we were proving trigonometric identities. Now we're just dealing with trigonometric identities where we have different angles inside. But you can see we just apply our formulas and we can get it down where we need it to just fine. Alright, so now we're going to start moving towards the half angle identity. Before we get there, we're going to have one little stop along the road. And this formula is for lowering powers. Basically, if you have cosine squared of a function and you want it only in terms of cosine of x as a nice simplification for the computer that is computationally less expensive. And so it is desirable to be able to know how to take an exponent off of a trig function. So we're going to use our double angle for cosines. And we're going to use it and make two separate substitutions to get two different formulas. One for cosine, one for sine. So the first one, we start off cosine of 2x. And we're going to substitute out our cosine using the Pythagorean identity. Like so. So 1 minus 2 sine squared x. And that's it. Well, no, I mean, that's not it, but that's our nice simplification. We want to solve this for sine squared, of course. So we've got sine squared of x equals 1 minus cosine of 2x all over 2 when we rearrange that equation. And that's our formula. And so note what it does. We have an exponent on our sine function, an exponent on our sine function. the formula takes that exponent and makes it go away, and it just expresses the function in terms of a double angle. Now let's do something similar, but we want to get, instead of converting from sine, taking the exponent off sine, we want to take the exponent off a cosine. So we're going to do the exact same trick. We're going to take cosine of 2x. We have cosine squared x, and now we're going to replace that sine squared with 1 minus cosine squared x via the Pythagorean identity. And so this simplifies over to 2 cosine squared x minus 1. And now we are going to solve for our exponent term there. And when we do that, we get 1 plus cosine of 2x all over 2. And that is our formula right there. Now, what's one way we could test our formulas? Make sure we didn't make a mistake along the way. Well, we know that the Pythagorean identity is cosine squared plus sine squared equals 1. So if we add these two expressions together, we should get 1. And if we do not get 1, we know we made a mistake. So let's go ahead and check it real fast. So we have 1 minus cosine 2x all over 2 plus 1 plus cosine 2x all over 2. And so you immediately notice that we have a negative cosine 2x divided by 2 and a positive cosine 2x divided by 2. So those are going to cancel. And so we are left with is 1/2 plus 1/2, which is 1. So it checks out. So good. All right, now let's go ahead and come up with a similar term for tan squared. Well, we know that tan squared is simply sine squared x over cosine squared x. And so, since we've already done the legwork early on, we're just going to apply what we have already done. Sine squared is 1 minus cosine 2x divided by 2. And then cosine squared x is 1 plus cosine 2x all over 2. And so you can see that the halves in each terms cancel with each other. And so we're left with 1 minus cosine 2x over 1 plus cosine 2x. And we're done. So you can kind of see how the theorems build on each other, making the next successive theorem typically easier than the prior one. Okay, so we're going to use all this. Let's go ahead and restate this as well. Tan squared we're going to go ahead and use half angles, or come up with our expressions for half angles, but we're just going to make the following substitution into what we already done. Where we see x, we're going to replace x with u divided by 2. So let's look at this expression first. Everywhere we see x, we'll replace it with u over 2. So we have sine squared of u divided by 2 equals 1 minus cosine of 2 times u over 2. And note that those 2's will cancel with each other, which gets us 1 minus cosine of u all divided by 2. So that is our formula, our half angle formula. And we can go ahead and put that square root on there, positive or negative. So there is our formula. Nice and easy. So let's do the same thing for cosine now. Again, cosine squared of u divided by 2, we're using this formula here, equals 1 plus cosine of 2 times u divided by 2, all divided by 2. Again, these 2's cancel with each other. Take the square root of both sides. So we have cosine u over 2 equals positive or negative square root of 1 plus cosine of u divided by 2. Now we do the same thing for the tangent function. Tan of u over 2 equals the square root of 1 minus cosine u over 1 plus cosine u. And of course the whole thing is square rooted. There we go. That's our formula. Alright, so pretty nice and straightforward once you get to this point. Alright, so let's do a pair of quick examples real fast, one using double angle and the other one using the half angle. Alright, so for A, we have cosine 2 times the inverse sine of x. And that's going to equal the cosine squared of the inverse sine of x minus sine squared of the inverse sine of x. Alright, and just for clarity, let's go ahead and put these squares on the outside of everything, like so. And let's go ahead and run through this. The right expression, of course, the sine of the inverse sine is simply what you see inside, so it's going to be x, and that whole thing is squared. Now, for the next one, let's go ahead and take a look. We're going to go ahead and look at the inside of this guy right here. We're going to let some angle theta equal the inverse sine of x, so that sine theta equals x divided by 1. Now this implies a triangle that looks like this. Right, so right triangle, here is an angle theta, and so sine is opposite over hypotenuse. We have an x over here, the hypotenuse is here. We can figure out the missing leg using the Pythagorean theorem. So we have the square root of x squared minus 1 is that missing leg. So note that, this guy right here that I've highlighted, that's our theta. And we're taking the cosine of that angle. So cosine, what is cosine? Cosine is adjacent divided by hypotenuse. And so the adjacent is the square root of x squared minus 1. And the hypotenuse is simply 1. So when we evaluate this guy further, it becomes x squared minus 1 well, I'm sorry, I got this backwards here. This should be 1 minus x squared. 1 minus x squared. There we go. And so when we work this through, this becomes 1 minus x squared here. And then that simplifies to 1 minus 2 times x squared. And look at that simplification. That's just a parabola. That's something that we can visualize in our own head. Whereas simply looking at this expression here, well, it's not obvious that it's a parabola. It is worth noting that this does have certain domain restrictions that are subject to the inverse function. But other than that, it's just a straightforward downward facing parabola. So now let's go ahead and take a look at the second one. And now we're going to use our half angle for tangents. 0.5 is a half. So for B, this becomes positive or negative square root of 1 minus cosine x. I'm sorry, the cosine of that angle, which is the inverse cosine of x over 2 over 1 plus the cosine of the inverse cosine of x over 2. And then that further equals, right, the cosine of the inverse cosine is just what you see inside. So this further equals the positive or negative of the square root (1 minus x over 2) over 1 plus x over 2. And that would be our final answer as well. All right, so not too bad. Just apply the formulas and then let the math take you where it will. All right, so now we're going to get to our last section of this handout, the product to sum formulas, and then we're going to do the sum to product formula. So as it turns out, oftentimes you'll have a product, the multiplication of two trigonometric values, and what we want to do is be able to convert that into sums, because that oftentimes this will lead to a big simplification of our expression. So let's start off with this first one. We're going to add the sum for sines and then the difference for sines. So sine of A plus B, or alpha plus beta, equals sine alpha cosine beta, and then we simply add. So we have cosine alpha sine beta. And so next we have the sine of the difference between these two angles. And so sine alpha cosine beta starts off the same. And then minus cosine alpha sine beta. All right, so let's go ahead and work this through. We have sine of alpha plus beta. All right, and you notice on the right-hand side that this guy and this guy cancel out, leaving us with 2 times sine alpha cosine beta. And so we want to solve this for the product of the two trig functions, because that's what we're the formula we're trying to get. So we have sine alpha cosine beta equals 1/2 sine alpha plus beta plus sine alpha minus beta. And there we go. That's our first of 4 formulas. And so let's go ahead and keep moving. The next one, note we're using the exact same formulas, but now we are subtracting instead of adding. So let's go ahead and set this up. All right, and this time we are subtracting the next guy. So minus sine alpha minus beta, and that's going to equal negative sine alpha cosine beta plus cosine alpha sine beta. And again, we're just writing out the angle difference formula that we came up with earlier. Note that the minus sign is now in the first term instead of the second term like we did before. That's because of this minus sign right there. Alright, so let's go ahead and perform this operation. On the left-hand side, sine alpha plus beta minus sine alpha minus beta. Note that right here, these two now cancel out, so all we're left is the next term. So we have 2 times cosine alpha sine beta. Solve it for the products. And so we have cosine alpha times sine beta equals 1/2 sine alpha plus beta minus sine alpha minus beta. And that is our next formula. 2 down, and now we have 2 more to go. Alright, so now we're going to come up with our next one, starting off with 3. Note now we're using the cosines instead of just sines like we were before. So cosine of alpha plus beta equals cosine alpha cosine beta minus sine alpha sine beta, then cosine of alpha minus beta and now it's a plus. And again, we are adding these, and so we get the following result: cosine alpha plus beta plus cosine alpha minus beta. And note that these two cancel, and so we end up with 2 times cosine alpha cosine beta. Solve for the products that we have right here, and so we end up with the following result: cosine alpha cosine beta equals 1/2 cosine alpha plus beta plus cosine alpha minus beta. Alright. Now it's time for the very last one. So even though there's, it seems kind of, tedious going through all that, there is definitely a pattern to each of these. And so once you identify the pattern, it starts to flow a little bit better. So here we have cosine alpha plus beta equals minus, and now we subtract out the next guy, cosine alpha minus beta, and so now basically everything that was positive is negative, everything that was negative is now positive. Of course, in this case they're both negative. Now and so you can see this is going to be the one that cancels out. And so when we add these together, cosine alpha minus cosine beta, alpha minus cosine alpha minus beta equals 0 minus 2 sine alpha sine beta. Solving for the products, we get sine alpha times sine beta equals 1/2 cosine alpha minus beta minus cosine alpha plus beta. And note that we distributed the negative that was hanging out right over here. And that's it. Those are our product to sum formulas. So again, we use these to take a product of two trig functions and to turn it into a sum of two trig functions. So now let's go ahead and move on to the sum to product formulas. This is where we have a sum of two functions and we want to turn it into a product of two. So note that we're going to be using the two, made up these two identities, alpha and beta. When we add these two together, we get x plus y over 2, x minus y over 2. Note that y over 2 minus y over 2 goes away, and so we're left with x divided by 2 plus x divided by 2, which of course is just x. So anywhere you see alpha plus beta, we're going to write x. Now let's go ahead and look at alpha minus beta. All right, distribute that negative to both of these terms. And so you can see that we've got x over 2 minus x over 2, so those are going to go away. And so what we're left with is y over 2 plus y over 2, which is just y. So everywhere we see alpha minus beta, simply replace it with y. All right, so let's take a look here. We have sine of alpha, which is simply x plus y over 2. Cosine of beta, which is x minus y over 2. We're going to go ahead and multiply both sides by 2 to get rid of that 1/2, so we have the 2 hanging out here. And so this is going to equal sine of alpha plus beta, which we covered as x, plus sine of alpha minus beta, which is simply y. And there we go, that's it. Now we've got a sum over here on the right-hand side. So you have a sum of two functions. If you want to convert that into a product, you just take the x and y values and use this part of the formula right there. All right, let's look at the second one. So cosine of, let's go ahead and revert, we're going to go ahead and multiply both sides by 2. Let's take care of this side first, right? So we've got sine of alpha plus beta, which we covered is x, minus sine of alpha minus beta, which is simply y. And that equals 2 times cosine of alpha, which is x plus y over 2, times sine of beta, which is x minus y over 2. And that's it. That's our formula. Now let's go to the next one. Again, let's write out the right-hand side first. And we're multiplying both sides by 2. So cosine of alpha plus beta is cosine of x plus cosine of y equals 2 times the cosine of x plus y over 2 times cosine of x minus y over 2. So a nice simple formula to convert the sum of two products into the product of two, the sum of two trig functions to the product of two trig functions. All right, so for the next one, again, start off with the right-hand side. Cosine of y minus cosine x which is going to equal 2 times sine of x plus y over 2 times sine of x minus y over 2. And if you want it to match the formula in the book, we can just multiply through by a negative so that we get cosine x minus cosine y equals negative 2 sine of x plus y over 2 sine of x minus y over 2. But either formula will work. You don't have to multiply through by negative if you don't want to, but that is the formula. Okay, that is it for the class. I hope this was helpful, and have a wonderful week. Email me if you have any questions on the homework assignment, and I'll talk to you then.